Thank you very much, Steve. Yes, this is Bob Card. Today we're going to be talking about DC to DC products and applications. And if anybody has any questions, feel free to email me at this email address, bob.card@onsemi.com. Okay, so I'm going to start off with a mini DC to DC tutorial. Then I'm going to talk about our LDO portfolio. Then I'm going to talk about our bucks and boosts, which is the DC converters, starting with the lower input, 2.5 to 5.5 volt. Then the higher input up to 30 volt inputs, and then I'll close it with our bucks and boosts that are above 30 volt voltage input. Then I'll be talking about some of these block diagrams, the application block diagrams. I'll probably be getting close to the end of the session. This is a lot to put into 1 hour, so the application block diagrams might run a little swiftly. However, since it's recorded and we're going to archive the slides in Sales Connect, please feel free to go there and download them and refresh them or go over it again. And if you also have any questions, you can always email me. So the first thing I want to talk about is Lenz's law. So many of the governing principles of DC to DC conversion stems from Faraday's laws of induction and Lenz's law. So basically, in this diagram here on the left, if I'm putting current into an inductor, you're going to have an expanding field as that current rises. I'm sorry, an expanding flux, electromagnetic flux. And you're going to induce a voltage that opposes the current increase. Okay, so you're going to have a polarity of a minus here and a plus here. So an increase in inductor current causes the magnetic field to expand. Likewise, if that current starts to decrease, the flux is going to then start to collapse. And the induced voltage then changes polarity because that induced voltage is opposing the change. So an increase in inductor current causes the field to expand, and decrease in inductor current causes the magnetic field to collapse. And the induced voltage, or the counter EMF polarity, opposes the change in the inductor current. You'll note that the current is always going in the same direction, whether it's collapsing or expanding, but the polarities do change when the field is collapsing versus expanding. So if I go and look at a buck, I have my V input on the left here. I have a high side on my low side set here. Then I have the inductor followed by the load. So I'm using PWM, or pulse width modulation, for FET control. I've got my Q1 high side and my Q2 low side. And the whole point of bucks is you're going to be duty cycling these Q1 and Q2. And Q1 is, while Q1's on, Q2 is essentially its complement. It'll be off and vice versa. And so with a 12 volt in and a 50% duty cycle, you're going to get a 6 volts out. So the theoretical V out formula is V in times D, where D equals the duty cycle from 0 to 1. And I just want to point out this is a theoretical V out because, well, I'm assuming an idealized converter at this point. All the components are considered to be perfect or lossless. We know that's not real, but for the sake of discussion right now, we're going to be talking about a perfect lossless scenario. Q2 is called the synchronous rectifier. And so originally, in early bucks for an asynchronous buck, this was a diode. It was replaced with a N-channel MOSFET because it's more efficient. And that became, then it was called a synchronous buck converter. And the synchronous rectifier is called the synchronous rectifier because it needs to be synchronized to Q1. Okay, so it's always tied to Q1. However, you never want to have both Q1 and Q2 turn on exactly at the same time because that causes what's called shoot-through current or cross-conduction. You want to prevent that because that's basically a short between V in plus and minus. So you insert these dead times. So when Q1 goes on, you turn Q2 off maybe just before that. And likewise, when Q1 goes off, you turn off Q2 a little bit afterwards. Getting back to the duty cycle, 12 volts in with a 75% duty cycle will yield 9 volts on the output, and 12 volts in with a 25% duty cycle will yield 3 volts at the output. Now remember, power is I times V on both the inputs and the outputs. So when you do the V out decrease with the duty cycling, and we sometimes call that a chopper, the I out increases proportionally. Okay, so that's the conversion. So when you have 12 volts in 6 volts out, you may have 1 amp on the input. You're going to have 2 amps on the output, and that's an ideal lossless scenario. There's always going to be some loss in there, and we're going to talk more about that. This also assumes constant current mode, or CCM. That's when the inductor current never reaches 0. We're talking fixed frequency, steady state. And then let's trace the current. So during the on state, we'll look at the current flow. So when Q1 is on, which is what's considered the on state, that's when you start energizing the inductor. You start building up a field, and it starts expanding, and you're storing energy. And this is really, inductor provides energy storage. So you're storing energy. You're also charging the capacitor, the output capacitor, and you're putting energy into the load. And then when Q1 goes off and Q2 goes on, now your load is being powered by the collapsing inductor. So those are the basic principles, assumptions, and takeaways for buck converter basics. Oh, also, so your V out's going to have some ripple because you've got all this switching going on. That can be decreased with increase in the C out, or increase in the frequency of the switching, or both. However, EMI can result from high switching frequency, so that's something you want to be careful of. And also the shoot-through current, which I mentioned earlier. So for a boost, now we move that inductor right up against the V-in, and now the high side, low side sets are in between the inductor and the load. So the theoretical formula on for duty cycling has changed. It's now V-in divided by 1 minus D, where D equals the duty cycle from 0 to 1. So if you have 6 volts in, 50% duty, you get 12 volts out. And again, you will have that power conversion. So if you have 6 volts in, let's say 1 amp, and then you got 12 volts out, then your current is going to be half an amp. Again, assuming perfect losses. And likewise, with 3 different scenarios, there's 6 volts in with a 75% duty, you've got 24 volts out, and with a 25% duty, you've got 8 volts out. Again, the inductor is providing the energy storage. You need to be careful to prevent shoot-through current. And let's walk through the current. Let's walk through the current flow. So when Q1 is on, with a boost, that's when we start storing energy in the inductor. So the field's expanding. And then when we switch and Q2 is on and Q1 is off, now we're dumping that energy through Q2 into the storage cap as well as the load. But note, this stored energy is in series with the V-in. So now we have 2 sources in series, and that's really what drives the boost. And then we go back to Q1 being on, which is the same state as here, but we also have a charge cap, output cap, and that'll get that'll discharge into the load. So that gives you some of the assumptions and takeaways of a boost converter basics. Put them together, we have a buck boost. Now we have FET control with 4 FETs. The 2 FETs on the left, Q1 and Q2, responsible for buck mode, and you'll see the resulting current flow. And then on the right, you have Q3 and Q4, and the resulting current flows, and that's the boost mode. So we also have the shoot-through prevention as well. So we want to make sure we don't do shoot-through between Q3 and Q4, and we don't want to do shoot-through between Q1 and Q2. Now, a quick note on voltage regulation, and this is just one example of voltage regulation. That's or output regulation, and that's with voltage. So sometimes you may see a buck. This example is our FAN 6500 series. It's a 10 amp buck, and it's got the integrated synchronous rectifier with the PWM control here. And you'll see it's got this feedback pin. That feedback pin goes to a resistor divider or ladder with the output. So this basically provides an attenuated voltage of the output that goes into the feedback. That goes into an error amplifier, and that's compared to a VREF. The VREF is an internal reference voltage, 0.6 volts plus or minus 1% over minus 4 to 125 degrees C. So that's part of what we provide. We do, so this circuit is trimmed at the factory at wafer fab, a wafer sort, to be able to display that kind of accuracy over time, over process and temperature. So that goes through into a comparator with the ramp on the other leg of the comparator, and that develops the PWM, or the pulse width modulation control, which gets level shifted and sent out and controls the high side and low side FETs. Meanwhile, there's typically three sources of power losses for DC to DC conversion. There's conduction losses, switching, and static. The conduction losses are basically driven by I squared R, which is to say those are DC level conduction losses, whether it's the RDS-ons of the high side, low side FETs, the inductor, or the equivalent series resistance of the capacitor, or the PCB traces as well. They all contribute to conduction losses. Now you also have switching losses, and those happen during the low to high and high to low transitions of the MOSFETs, which results in a dV over dt. You also have core losses in the inductor, and then there's also losses to the gate drive. There's a lot of capacitance associated with gate drive, and you need to charge and discharge those the capacitances of the FETs, and that dissipates power as well. And then finally, static losses, which are basically the control circuit and the feedback circuit. So we mentioned CCM, which is continuous conduction mode, which is where that current, that IL, never hits 0 amps while you're doing Q1 is going on and off. Okay, so that's the controller implements the PWM to duty cycle Q1 and Q2 to determine the output voltage. And this is typically seen in medium to high loads, CCM. However, a very light load can force DCM, discontinuous mode, which introduces higher switching losses. A different control technique called PFM can be used to minimize these losses. So PFM is pulse frequency modulation, with a control out, you control V out by varying the frequency at a given duty cycle. So let's summarize that real quickly. So CCM is IL never drops to 0 amps. DCM is IL drops to 0 amps. PWM, you control the V out by varying the duty cycle at a given frequency. And PFM, you control V out by varying the frequency at a given duty cycle. There's other schemes to control, and there's other things. I just want to make you, just sort of define these. Another thing I want to define is dynamic voltage scaling. Many of our devices do this. Let's say you've got a buck or a boost, and you program it to go from one voltage to another, V1 to V2. You may not want to step immediately to that second voltage. That may cause a lot of ringing or oscillations. Essentially, with these products, you've got L's and R's and C's. So you've got tank circuits there, and so you could have oscillations and ringing. So to prevent that, internally, some of our devices automatically or autonomously introduce steps, both in time and voltage, to go from V1 to V2, and likewise for going from a higher voltage to a lower voltage. This is just called DVS, or dynamic voltage scaling. So let's quickly talk about the basics of an LDO, which is a little different than a DC to DC. And at the heart of an LDO is a MOSFET. It could be a PMOS or an NMOS. In this example, I've got an NMOS. And I've got 5 volts in the input. I've got 3.3 volts on the output. And therefore, I've got a dropout voltage, or a VDS, drain to source, of 1.7 volts. So in this example, I've got 5 in, 3 out, 1.7 volt VDS. If my load is 500 milliamps constant, that puts me at a VGS of approximately 3 volts. I get that from looking at my N-channel MOSFET operating region. On the x-axis, I've got VDS. On the y-axis, I've got my drain current, or my load current. And you can see 500 milliamps intersects with 1.7 volts at a VGS of approximately 3 volts. So this gate drive needs to be about 3 volts to put 500 milliamps out to this device. The way it does this control, it's got an internal attenuation circuit here. These 2 resistors on one end of the one leg of the input of the error amplifier, plus a trimmed VREF at the other. And this error amplifier is going to do everything it can with its gate drive to make these 2 equal. So that's basically your feedback mechanism for maintaining a solid output independent of the input changing and independent of load stepping. So Q1 will equal 3.4 ohms, and that's simply Ohm's law. That's the VDS, so 1.7 over the 500 milliamps. The power dissipation, again, is Ohm's law, I squared R, or 850 milliwatts, which is 500 milli times 3.4 ohms. And the efficiency is 66%, which is P out over P in, 1.65 watts over 2.5 watts. Well, you can see that efficiency, isn't so great. But before I go into that, I just want to summarize. The error amplifier modulates the gate drive, the VGS, such that the attenuated V out agrees with the VREF that's factory trimmed for accuracy across process and temperature. So unlike DC to DC, LDO output current equals the input current, right? So that is a difference. And really, in a way, it's not different because what happens is the power gets dissipated in the FET, okay? A lot of power gets dissipated in the FET, and that's why it's not that efficient. I kind of look at LDOs at a high level. I look at this MOSFET as a variable resistor. And this control loop is varying the VGS to put a different voltage drop across the resistor such that the output will always be what it's supposed to be, in this case, 3.3 volts. One quick note, if the delta V in versus V out, or that's also called the dropout or the VDS, is low, then the efficiency does go up, and if it's high, the efficiency goes down. So in that previous example, we had a VDS of 1.7 volts for a 66% efficiency. If you change that VDS to half a volt, let's say 3.3 volts in, 2.8 volts out, our efficiency goes up to approximately 84%. So LDOs have really great benefits, okay? They're excellent response to load transitions, okay? Because you've got this analog loop that's tightly coupled. You've got excellent output voltage accuracy because these resistors in the VREF can be trimmed at the factory. You've got excellent power supply rejection ratio, PSRR, and noise performance. So if you have a ripple on the input, this device, if it's designed properly with the error amp and the gate drive and the trim, you can highly attenuate that input noise and make sure it doesn't get to the output. And that's a big advantage of LDOs. It's got a very small footprint, therefore inexpensive, and no need for an inductor. So a lot of benefits for an LDO. And I want to quickly introduce On Semiconductor's NCP 160 series, the 60, 61, 63, and 67, each having different current capabilities depicted in this row here for the output current. But I want to really highlight the blue section here, and that is the power supply rejection ratio in dB at 1 kilohertz is well over 90 dB. That's world-class performance. It's definitely very difficult to beat that. It's a very difficult thing to do, and we do it well. And then also we have very, very low output noise, 10 and as low as 6.5 microvolts RMS. So a lot of good reasons to consider our parts, and we also have a very wide temperature range for these. So we really have some excellent, excellent LDOs. Now for charge pumps, that's a little bit of a different approach. It's a DC to DC conversion. I'm going to show you two examples, a divide by 2 on the left and a multiply by 2 on the right. Basically, you have this switch configuration, 4 switches, and you have a flying capacitor that's external. In effect, the flying capacitor provides the energy storage that's done with the inductor with the switching buck and boost. So basically, if you duty cycle these FETs, so Q1 and Q3 are paired, Q2 and Q4 are paired. When Q1 and Q3 are on, you put the C-fly in series with C2 over here, and you put that across VN. In this case, VN is 12 volts, and each one of those devices will charge, each one of these caps will charge to VN divided by 2. Then you switch them and put them in parallel, and you put that out to the load. And so now you have a 6-volt load, 6-volt output, but you also have twice the current, right? You have twice the input current because you've divided the voltage in half. You've got that, and that's an ideal scenario, of course. There are some power losses, so it's not exactly twice, but it's you do, when you cut the voltage in half, you double the current. A multiply by 2 charge pump has a different configuration for the switches, still has the flying capacity for energy storage, but now when Q1 and Q2 and Q4 are on, you have VN across C-fly, and then when Q2 and Q4 are off, now you have C-fly in series with C2, which puts out a 12 volt, which doubles the input. So now you have, for example, 6 volts in, you'll have 12 volts out, and now your output current will be 1/2 of the input current, thereby maintaining conservation of energy. So I'm going to pivot a little bit, and I think about IoT a lot. We all have had to. It's been a kind of a theme going on the last couple of years, and it's harder to say what's not IoT than what is IoT. But what you can say is that for the most part, IoT, how IoT is powered can be divided into two groups. Either you're grid powered or you're off-grid powered. So if you're grid powered, you're powered through AC/DC or PO, wireless charging. The point being, in my mind, it's sort of somewhere behind this outlet. If you trace the wires far enough, you'll get to a windmill or a solar array or a nuclear power plant or a big dam or Niagara Falls, what have you. You've got a pretty much an unlimited power supply, arguably. Not the case for off-grid. So off-grid, you're typically battery powered. You may have energy harvesting. Again, solar's, you may have solar, which is, but if a cloud goes by the sun, you're not guaranteed a power all the time. And same with smart passive sensors. Those are energized by the RF of the device. So for off-grid power, we tend to prioritize low IQ. For grid power, we tend to prioritize efficiency. They both matter. Okay, I'm not trying to say low IQ doesn't really matter in grid powered, but I tend to prioritize efficiency more because you've got higher power for one, and as you dissipate power, you generate heat, and there's this big market movements for high density and ultra high density power supplies. So you've got to really look at efficiency as a big driver for grid powered. Quiescent current, which is basically the standby current, not to be confused with shutdown current. A lot of times for IoT battery powered, you're going to have some sort of MCU that's asleep. It wakes up, does something, and then goes back to sleep. That's very common. Well, while it's sleeping, you don't want to be burning a lot of power. Last thing you want to do is deplete your battery while it's sleeping. So low IQ, devices that have low IQ are going to make that battery last longer. So for low IQ LDOs and bucks for off-grid, we have the NCP171 and the NCP170 LDOs, followed by the FAN 53713 buck. So this first LDO, the 171, it delivers 80 milliamps in mission mode, but if the load is 5 milliamps or lower, it only consumes on its own 50 nanoamps of IQ, which is basically ground current coming up. So think about that. When you've got an IoT edge node that's battery powered, it's sleeping, let's say 99.9% of the time. A lot of MCUs now and SoCs and ASICs, one of their big claims to fame is multiple levels of sleep mode. And certain things are powered up and running during different levels of sleep mode. The whole point is that sleep load is typically less than a couple of milliamps. So this is a great device to use for a battery-powered IoT edge node because when your MCU is asleep, this is hardly burning any power at all. I mean, 50 nanoamps is barely measurable. Again, we've got the 70, which has a mission mode of twice. The 171 goes 150 milliamps, and its IQ, quiescent current, is 500 nanoamps. And then we've got the 53713. So if your MCU or device wakes up and you need more power, you need an amp or an amp and a half, we've got this device, and it only sinks 2 microamps of quiescent current when its load is under 5 milliamps. So 3 really good solutions for the wake, sleep, duty cycling of battery-powered IoT edge nodes. And then for on the grid, we've got some excellent efficient bucks. We've got the 1.5 amp 53713, which depending with a V out of 1.8 volts, depending on its input, it's got 90% efficiency going as high as 93. We've got the FAN 65008B, which reaches 98.5% efficiency, depending on the with a V out of 24 volts with different voltages coming in. And then finally, we have a 20 amp buck regulator, which takes a 7 to 18 volt input and puts out 20 amps. And it peaks up at about 92% efficiency based on the load. So 3 examples of on-grid, highly efficient devices that you consider using. And then finally, we've got a very efficient buck boost. We use this for our USB products. that needs to put out a 5-volt to 20-volt rail. And you can see from 9 volts to 20 volts, from a ½ amp, we're above 90% efficiency. You go to 1 amp, we're above 95% efficiency. And when you go out to 3 amps, we're about around 97 to 99% efficiency. The 5-volt out, which is going to be a little less efficient, hits 95% at 3 amps and hits 90% at 1 amp. So a very good solution, buck boost solution, is the NCV 81599. And then finally, to summarize, and I really recommend hanging on to this particular slide. This is a nice summary. I look at LDOs, charge pumps, and DC to DCs, compare their efficiency, the space, power supply rejection, and noise. I group those together. The loads that they service. So LDOs are really good for smaller loads, typically tens of milliamps to hundreds of milliamps. Excellent PSSR and noise rejection. Very small, very low cost, low IQ, no EMI because there's no inductor. However, they're low in efficiency. So, they make sense where they make sense. If you want to go a little bit higher in efficiency, the charge pump is kind of a midpoint or little bit, I should say, closer to the DC to DC in efficiency. It's got medium, takes up more space, but not quite as much as the DC to DC. Similar PSSR and noise, similar IQ, medium cost, and no inductor. So that lowers the cost a bit because those inductors can be expensive and they're pretty big and they're tall. And DC to DC is the highest cost, highest EMI. It does have the inductor, but it gets you to tens of amps, right? So if that's what you need, you don't have much of a choice. So this is a nice summary. And one key thing I want to reiterate, better efficiency means less heat dissipation. So I'm going to do a quick hypothetical power distribution exercise. I'm going to assume 48-volt input rail. We're going to build a power tree. I've got 9 loads. These 9 loads have a range of VCCs from 1.2 volts to 12. They draw a certain amount of current. I've tallied up the worst case power out of each data sheet, and I summed it, and it's 131.4 watts, okay? None of these devices require an LDO for high PSRR or low noise except for one rail, and that's on my camera, which is an image sensor, and that's the 2.8-volt rail. When you think about image sensors, what I picture is a parking lot filled with millions of A to D converters, and some of them are 12, 14, 16-bit A to D converters, so you don't want their least significant bits bouncing around with noise. That's going to make your pixels fuzzy. So optionally, you can put a bunch of decoupling near the chip, but that's only so good because the chip is fairly big, and it's hard to decouple well when you've got such noisy potential. So you can also put MIM caps on the chip, but that does increase the cost. So typically, image sensors like to see an LDO, which has really good power supply rejection, and it really gives you a really good DC level of 2.8 volts. Okay, so with this hypothetical, I've got 48 coming in. I'm going to have one buck that's going to drop it down to a 12-volt rail. That 12-volt rail is going to service my 2 stepper motors here, and it's also going to go to this buck boost. Then I'm going to drop down to a second rail, which is the 3-volt rail. That's going to provide my Wi-Fi, BLE, and my LCD. And then it also, that 3-volt rail also goes to an MCU, and it's going to go to a boost for my Type A connector for VBus, and it's also going to go to the LDOs for the image sensor. So I'm going to start. So you can do it different ways. You can add up all your loads here and work your way towards the front, or you can start at a big number and work your way towards the back, and then see how it works. So I'm going to walk through it, going from the front to the loads, from the incoming 48-volt rail all the way to the loads. We'll just walk through it. So the first buck, I've got a 92% efficiency that wants to do a 12-volt rail. So right away, with 200 watts coming in, I'm down to 184 watts just based on the 92% efficiency. If I look at my 2 motor drive loads, if I factor those in, now I'm down to 164 watts. I bring that over into my next branch, if you will, which is my buck boost, which is this guy here going to the Type C. That's going to want 100 watts, worst case. It's not, it may not ever use all these worst case powers, but you do have to design for it. So So I lose some, so I derate my, my initial power for 95%. I take out 100 watts, and now I'm down to 55.8. I go to my next branch, which is buck 2. That's a 3-volt rail. I've got 55.8 now remaining. I derate that for 91%. That gives me 50.78. I subtract out my load, my worst case loads. Now I'm down to 49.8. I bring that into my boost rail, which is the type A connector right here. And that's going to need 10 watts worst case. Now I'm down to 35.8, so on and so forth. And you can see once I deliver my 35.8 watts remaining to my LDOs for the camera, and I divvy those out, and now I'm left with 12 watts. So basically, starting with 200 to service 131.3 watts worst case, I've got 12 watts left over. So I just wanted to walk through that with you. And so this is what I would put together for using on semiconductor devices. So all the devices in green are on semiconductor devices. I'm starting with the fan 6500, the 65005A. These are 8 amp bucks, very efficient, and they can be tied together. It's sort of like a multi-phase scenario. One's a master, one's a slave, and the clocks sync up together, and that allows me to provide a 12-volt, 15-amp rail. That goes to the fan 23SV 20-amp buck, 91% efficiency. I've got RSL10. I've got a boost here, the 48623, 2.5 amp boost. I've got my buck boost that I mentioned before for Type C. Great solution here. Got these beautiful NCP163s with a PSRR of 95 dB. And I've got our image sensor here, and then our stepper motors. So one quick message I want to make. We're really good in DC to DC, but we're also very wide. We make a lot of, we're wide and deep. We make a lot of products. And part of this training is to try to convey and communicate that to you. So we also have a number of industrial LDO, our industrial LDO portfolio. This slide breaks it down by applications. So we have wide input LDOs, 20 VINs up to 24 volts and even 450. We've got low IQ LDOs. I've already mentioned those, the 170 and the 171, 500 nano and 50 nano respectively. We've got RF, which is like the 163. I mentioned that. Got 95 dB of PSSR, and we also have some high current LDOs. So a lot to choose from with On Semiconductor. And then also we've got a really wide portfolio of automotive LDOs too, which is worth looking at later at your leisure. So now let's move on to the DC to DC. I'm going to talk about, we sometimes call it point of load with the VN under 5.5 volts. I have these products starting at 0.5 amp out to 5 amps. And different topographies, buck boost, and boost with bypass. Many of these are CSP, and I've got a few QFNs here. So we'll talk first about the CSP devices. And my CSP devices are all captured here, all on target in production. I'm specifically going to talk about the FAN 537 series initially, but yeah, I've got the IQ and the IST here. I've got the I-outs here. So the I-outs range from 5 amps down to 300 milliamps. And then also you note the high-speed switching frequencies. So we go as high as 6 megahertz. Again, the higher switching you can do, the smaller your part count can be. So your inductor can be smaller relative to the amount of load you have. And your input and output capacitors can be smaller. And again, these CSPs are very small packages. If you're a little bit averse to a CSP, we also have some really nice QFN devices. This is our 3x3 NCP 3133, 31 family. So we've got the 3133, which puts out 5 amps. The 3135 puts out, 3133 puts out 3 amps. 3135 puts out 5 amps. 3136 puts out 5 amps. And these are all 3x3 millimeter QFNs. These are synchronous rectifiers. The high side, low side FETs are integrated. It does all the PWM inside. It goes up to 1.1 megahertz switching to reduce the size of the passes. And it's got that internal 0.6 volt reference of 1%. And then we've also got the NCP 1594, and that has a wider input range of 2.9 to 6 volts. And these had preset outputs, or externally adjustable from 0.6 to 90% of VN. And these switch from 500 kilohertz up to 2 meg. And these are 4x4 thermally enhanced QFNs. So it's got the exposed DAP here for, these exposed DAPs are great for, transferring the die temp onto the PCB interplanes. That's great. And that's a 4 amp device. And then we also have a number of boosts that are in CSPs, 95% efficiencies, high switching frequencies, a wide input range. Again, this is all, these parts right here are, max input of 5.5 volts. So typically, these are devices that would probably be facing a 1S lithium ion cell. And then we've got a very varied amount of output currents as well. And one example is the FAN 4861. This has a 2.3 to 5.45 input range, up to 92% efficiency in a small CSP package, 1.2 by 1.2, so very small. Excellent response to transients. So for a step of 500 milliamps, we've got 140 millivolt change in V out versus 200 millivolt change in V out. So that's good. And then we also have a couple of buck boost converters for these lower input voltages, the FAN 49100 and the FAN 49103 for you to take a look at. The FAN 49100, you can see very flat efficiency all the way across. So it doesn't drop down as the load drops. And again, that's starting to become more and more important with customers. So that's a feature, that's an added value. And efficiency up to 96% here as you get tired towards the load. A very compact device, 1.6 by 2 millimeters, and efficiency up to 96%. So that's good. And then we also have PMICs. I've got the NCP 6922. This has 2 bucks, 2 LDOs with, so the LDOs go from 1 volt to 3.3 volts and 50 millivolt steps, and the DC to DC goes from 0.6 volts to 3.3 volts in 12.5 millivolt steps. So a lot of, with I2C flexibility for the I2C programming, so a lot of flexibility with these devices. And then we've got a larger PMIC, which is the FAN 53880. This has 6 outputs ranging from 0.6 to 5.7 volts. So 1 buck, 1 boost, and 4 low noise LDOs, typically 35 microvolts RMS, and they go up to 300 milliamps. So a lot of options for when your inputs between like 2.5 volts and 5.5 volts. Now to move to higher input devices, these are asynchronous bucks with VNs going up to 30 volts. So you can see we've got a number of different topographies on the x-axis and the output currents on the y-axis. So we go up to 40 amps with the NCP 3296. Everything in green is in production, and in dark blue is with the dots of sampling, and dark blue is in development without the dots. So one of our workhorses is the NCP 323 series. We've got the 31, the 33, the 32, and the 35 over here on the right, on the bottom, all of which are on target in production. They have various inputs, either 4.5 to 18. You got the 33 has a wider input, 2.9 to 21 volts. That's a 20 amp device. The 31s are a 25 amp device. And for 15 amps, we've got the 32 and the 35 with a 4.5 to 21 volt input. And these have low side FETs are 1.5 ohms to 2 ohms to 4 ohms, and then the high side FETs are 7 ohms, 4.8, and 8 ohms. The lower the RDS on, the lower the conduction losses are when your parts switching. It goes up to 1 megahertz, 500 kilohertz, and up to 95% efficiency. And a nice thermally enhanced 6x6 millimeter 40 pin package here you see. It has the die exposed paddles for relieving the die temp into the PCB interplanes or even top layer. And then this is a quick look at the family differences between the 30, 31B and the 32 and the 33 and 35, the different currents. They all share the same packages, slightly different input voltage range, and also slightly different frequency selections. So that's available to you when you build your own power trees. And that's a big part of, the learnings of this presentation is to be able to build your own power trees for your customers quickly and make them accurate and solid. So here's some of the efficiencies for the 3231. For 12-volt in, you can see that we're hovering well above 90, at 95% efficient across a pretty wide load for certain V outs. And then we've got a V in of 5 volts. And you can see for other V outs, we're well above 95% efficiency. So definitely something, like I said, for grid power devices, it's all about efficiency. And then we also have the NCP 3284. This is a 30-watt single-phase voltage synchronous buck voltage regulator. It has an enhanced ramp pulse modulator control architecture, and it provides ultra-fast load transient response, which is captured on the next screen. So for our competitor, we're emulating. Well, it's not really emulating. We actually did a screen capture, but we go from a 1 amp load, we step to a 9 amp load, and then we step back to a 1 amp load. And we measure the V out, transient. So for the competition, that transient's more about 150 millivolts, and for our device, it's closer to 70 millivolts. So definitely really good performance for the transients, and that's important for products in your power tree. For products downstream, you don't want to cause, you don't want one load to affect an adjacent load that's on the same rail. And then we also have the FAN 23 SV XX. So XX translates to either 4 amps. So a 04 would be the 4 amp version, a 06 would be the 6 amp version, and it goes 10, 15, and 20 amps, and so on. Again, synchronous rectifier. So the high side, low side FETs are integrated. The inductors out here uses a small inductor of 0.47 microhenry. This goes from, like as I said, 4 to 20 amps, over 95% efficiency over a wide load range, and a V out from 0.6 to 12 volts. And here's some efficiency plots of that. Again, over 92% efficiency given with a 12 volt in and a 1.2 volt out at 500 kilohertz. And then we've got the medium voltages. So this is now, this is the buck boost for up to 30 volts input. So I've got the NCP 81599. We have the V version. So when you see a V at On Semiconductor right here, that means automotive. That's 4.5 to 32 volt operating range, 28 for the P version. Its frequency range is 150 to 1.2 megahertz. Seamless transition between buck and boost. It uses external FETs here. So you can size. What's nice about that is you can size your FETs for the amount of current you want to go through here. And we use this for our USB, a lot of our USB products, and I covered that in the last 2 weeks ago. I did USB, so feel free to download that and watch the recording. And I have a lot of information on this buck boost there, but I wanted to touch on it here. And it's got protection for over voltage, under voltage, and over current protection, and then 2 independent current sensing pins as well. And that comes in a 5x5 millimeter package, QFN. And again, these are the efficiencies. I've showed you this already. Just to reiterate, at 1 amp, we're above 95% efficiency for these voltages. And for 5 volts out, it crosses, at 1 amp, it crosses a 90% threshold for efficiency. And at 3 amps, you're at 95%. And the other voltages are, almost from 97 to 99% efficient. And now we get into the higher voltages, the VINs, above 30 volts. I've got the FAN 6500 here. So I've got voltage on the x-axis and current on the y-axis. So we go up to 10 amps, up to 80 volts. I've got the FAN 6500 series, 4.5 volt. I love this device. It takes an input of 4.5 volts to 65 volts. I can do 6 amps, 8 amps, or 10 amps. Programmable frequency of 100 kilohertz to 1 megahertz. Output voltage can be from 0.6 to 55 volts. How versatile is that? Plenty of protection. And then what we have is the suffix. The B suffix is that FETs are optimized for high duty cycle ratio, in other words, a high V out. And the A suffix, the FET is optimized for low duty cycle ratio, In other words, the low side FET is larger than the high side FET. So it's a really great idea. That way you can buy the A or the B depending on your how much you're bucking down. So you can see we're, you know, up to 96% efficient with 5 volts out here. We're at almost 90, over 98.5% efficient with V out at 28 volts. And we're at over 90, about 97% efficient with a V out of 5 volts here at 300 kilohertz. And then we're at 90, almost 98.5% efficient with a V out of 28 volts. So a lot of great options there. I really like that part, and it's selling very well. The NCP 4060, that's our 80 volt device. So it takes an input from 8 volts to 80 volts, a 6 amp output. It's got load protection as well. It's got the adjustable voltage down to 1.25 volts with plus or minus 1.5% accuracy. So a very nice device if you need to go above 65 volts. We've got the NCP 4060 that goes up to 80 volts. And it produces output voltage of 1.25 to 60 volts, up to 6 amps. Also a thermally enhanced package. You know, you always want to look for that, these higher current devices. So now I'm going to wrap it up with some application block diagrams. Like I said earlier in the beginning, I'm going to go through these pretty quickly, and feel free to reach out if you have questions. The first one is dear to my heart. This is a remote BLE keyless entry application that I did. So you have 2 options. So both cars have a bunch of ECUs, electrical control units that control your windows, your trunk, your roof, your seat, and blah, blah, blah. Well, this one controls your door lock. And you want to be able to open your door lock either directly with a phone through BLE or a cap touch with your door handle and your key fob, which has BLE in it. So that was basically the idea. So this device, this ECU here, is always listening, right? So it's got to be, it can't burn a lot of current because it's always listening because, you know, you're away. So this solution that I came up with is 58 microamps of always listening current. But before I mention that, one of the difficulties with any ECU is that it faces the battery, okay? The car battery. And the car battery has a thing called cold start and also load dump. And cold start can be such that in cold weather, when you go to turn your engine, that voltage can drop a lot due to the cold weather. And it can drop as much as from 12 to 3 volts. And this is typically a fairly well agreed upon sort of worst case scenario for cold start. And then the load dump can go as high as 45 volts. So we have a number of devices that can face the battery, put out certain amount of power, different types, and they have VBAT operating ranges. This device goes from 3.7 to 3.6. This device goes from 6 volts to 28 volts, but I like this NCB 48220. It's an LDO charge pump boost converter. It's a combination charge pump LDO, and it operates, it puts out a constant 5 volts or 3.3 volts, whichever you choose, with an input going from 3 volts to 40 volts, which covers you in this cold start load dump scenario. So it's a really nice device. Here's the block diagram. Here's my ECU. I've got the NCV 48220 LDO charge pump here, facing the battery. I've also got a LIN transceiver, because we make in-vehicle networking as well. We do LIN, CAN, and FlexRay. This one is LIN. This is our automotive BLE device, the NCV RSL10. And this is our that LDO, the NCV 8163. And these all burn very little IQ, and a total is 58.2 microamps. We also have, so this is a one slider on the NCV 48220, the 150 milliamp boost charge converter that takes an input from 3 to 40 volts. And then this is also a block diagram for wearable. I've got my 1S battery. We've got everything in green is what we make and sell. So again, my message is, you know, we go wide and we go deep. So we've got battery protection. We've got an excellent fuel gauge. We've got a standalone charger that faces the Type-C port. We've got all the LDOs for powering many different devices. We've got haptics as well, LRA and ERM haptic drivers. We've got a full family of capacitive touch, and we've got serial flash and SRAM, also OLED drivers. And this is a drone electronic speed controller, or ESC. So So your drones are going to have anywhere from 4 to 8 motors, and those are brushless DC motors. And we drive those with a flight control going into a processor that does a PWM and has the iSense. And I have 3 individual gate drivers, the NCP81080 that drives individual FETs with the current sense. The FETs are the NTF S4 CO8s. And we do current sensing. These are really great devices, super accurate, real easy to use. You know, can measure the voltage across 1 milliamp very accurately, so you don't dissipate a lot of power. That tells the processor, you know, what each leg is doing in the BLDC 3-phase. We also have circuitry, and this is my block diagram for the gimbal, main camera, and BLE. This is 4S now, going down to $2 for 5 and 9 volt rail. These stepper motors can drive the roll, pan, and tilt of the gimbal, as seen here. And then we've got a couple PMICs to drive the image sensor, as well as other circuitry that I've described. And then I've got a PoE security camera. In this case, I'm using 802.3 AT, which is 40 watts. We do have the BT devices that go as high as 90 watts. This particular device has an integrated DC to DC. So I've got a buck here that takes it down to a 5 volt rail, and I supply the rest of the circuitry. And I have I have a dual stepper for the pan tilt and a single stepper for the zoom here. And I've also got a security camera with an AC to DC power supply. So I've got my green bridge here, and this is a full wave rectifier, and it's a little more efficient because instead of silicon diodes, the green bridge FDMQ80205 uses N-channel MOSFETs. That feeds into our NCP1568 active clamp PWM controller on the primary side. I'll be talking about this on Thursday. This is one of our really nice, our most efficient bang for your buck active clamps. That also drives a half bridge, the NCP51530, which drives this FET right here. This FET, basically what it does is typically, sorry, I just dropped my microphone. So this FET here controls the snubber, which recycles the leakage energy from the primary side. When this FET turns off, it recycles it back into the load. I'll talk about that next week. And then this is a secondary controller, the NCP4306. I'll talk about that Thursday. And this goes down into more power tree of the temp sensors, LDOs, serial flash. We also have video processors. We make our own video processors that are paired with our image sensors, and we've got a 2.5 gigahertz MIPI switch. A lot of these image sensors now are using MIPI for their protocol for moving data back and forth. And so this is a 2-camera solution. I've got the ARO 430 for my cameras, the APO 200 for the processor, and I've got dual stepper motors for pan tilt and single step motors for the zoom. And then I'll wrap it up with rear view versus surround view automotive. So rear view, you typically have a camera here. You're going to do your image processing with the sensor. You're going to have your power shrubbery here, and it's going to be powered either through a coax or battery connected. In contrast, you've got surround view, where you don't do the processing at the camera. That gets shipped with a serializer through a cable to a fusion box. This is where your NVIDIA chips might be, and they're going to do central processing of the 4 cameras to do intelligent ADAS. So for rear camera view, again, the processor is with the image sensor. We do both processors and image sensors. This is a 3.2 megapixel image sensor. The PMIC driving that. We've got protection facing the battery. We've got bucks, a buck for the battery. We've also got a buck for power over coax. We've got in-vehicle networking, common mode filter with ESD protection, and also even level shifting, all automotive grade. And for surround view camera, we've got with a PMIC, again, the processor is centralized, so it's not in this image here. A lot of the same cast of characters here. And then I replaced the PMIC with the LDOs, and that's it.